All right, 4.6 on the mean value theorem. The mean value theorem is actually pretty straightforward. If a function is differentiable on an interval, then it is also continuous on that interval. Must be, in order to be differentiable. Therefore, the mean value theorem says that then there exists a number c between a and b such that the tangent line approximation, right, the tangent line slope right here, has to be equal to the secant slope somewhere between A and B, right? So here's the secant line slope, right? The average rate of change there. That means that somewhere along this interval, somewhere along here, the function has to have the slope of its tangent line equal the slope of that secant line. And it looks like it would happen in more than one place here, right? But at least one spot between A and B, there must be a value c such that f prime of c is equal to f of b minus f of a over b minus a. Okay, all that means is the tangent line slope has to equal the secant line slope somewhere on that interval. All right, so let's take an example. The example here looks like it has to do with x plus 1 quantity cubed. So what we want to do is we want to find the average rate of change on that interval. Okay, average rate of change on that interval will be the slope of the secant line. So the slope of the secant line will equal f of 1 minus f of negative 1 over 1 minus negative 1. Okay, f of 1 will be 8. F of negative 1 will be 0 over 2. Looks like our slope is 4. So we want f prime. Of course, we got to find f prime. We want f prime to equal 4. Right? We want the slope of our tangent line to equal 4. And we want to know what x value that'll be. That'll confirm for us c. So the derivative of the following function would be 3 times the quantity x plus 1 squared. Chain rule, the inside would just be times 1. So we want that to equal 4. Well, that would be 3 times the quantity x squared plus 2x plus 1, which would then give us, if we expand, 3x squared plus 6x plus 3 equal to 4. Unfortunately, it looks like we're not going to be able to factor. So we'd have to use the quadratic formula. And the quadratic formula yields two answers. It yields x equals negative 1 plus or minus the square root of 48 over 6. Now only one of these answers is correct for c. Because of this interval from negative 1 to 1, this negative answer is gone, and so then c equals negative 1 plus square root of 48 over 6. Alright, therefore f prime of negative 1 plus square root of 48 over 6 would have to equal 4. Alright, let's do another example. It looks like example 2 and example 3 are very similar, so I'm just going to do example 3. Find a value c such that f prime of c equals f of b minus f of a over b minus a. Okay, that's just asking for where is the slope of the secant line equal to f prime of x. Okay, so f of b minus f of a. So f of 1 minus f of 0 over 1 minus 0. So f of 1 is 1, f of 0 is 0. So it looks like the average rate of change on that interval is 1. The derivative of f of x, right, this would be x to the 1/3 power, would be 1 over 3x to the 2/3. Okay, you can work that on the side if you need it. Okay, so I want 1 over 3x to the 2/3 power to equal this 1. So I'm going to cross multiply. I'm going to divide I'm going to cube both sides. Okay, cube both sides. That one does that. So I get 1 over 27 is equal to x squared. Now that will mean that x equals plus or minus 1, square root of 1 is 1 over root 27. Now again, our interval here is from 0 to 1, therefore we can scratch the negative, and it looks like c will equal 1 over root 27. Therefore, f prime of 1 over root 27 would equal what the slope of the secant line is, which is 1. Okay, on this problem here, oh my gosh, that just got really small. That was cool. Okay, on this problem here, we've done A and we've done D before. A uses the intermediate value theorem. When you're given an interval like this and asked for some output, that's intermediate value theorem for sure, like every time. The two things we do need to know from that problem, which we did a few days ago, is that h of 1 equals 3 and h of 3 equals negative 7. We're going to use that on the next part, on part B. Explain why there must be, right? The functions f and g are differentiable for all real numbers and g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by h of x equals f of g of x minus 6. Explain why there must be a value c between 1 and 3 such that h prime of c is equal to negative 5. What I would do here is I would simply find the slope of the secant line. If I find the slope of the secant line on that interval, I would be taking h of 3 minus h of 1 over 3 minus 1. Well, h of 3 was negative 7, h of 1 was 3, over 3 minus 1, which is 2, so I see I must have a negative 5 somewhere in that continuous differentiable function. So I got to write my therefore statement. Therefore, by mean value theorem, there must exist some c between 1 and 3 such that h prime of c equals 5 because the slope of the secant line equals 5. Oops, I'm sorry, negative 5 because the slope of the secant line equals negative 5 on the interval 1 to 3. Alright, that would be a statement that you must make. This is not enough right here. You can't just get to negative 5 for the slope of the secant line. You have to say, by mean value theorem, there must exist a c between 1 and 3 such that the derivative equals negative 5 because the slope of the secant line equals negative 5 on that interval. Alright, part D we had also done on a previous homework set, so we're not going to do that. Okay, so let's look at the last two problems here. Example 5. Here's a table of values. The function f is continuous and differentiable on this closed interval. Mean value theorem may work here. Okay, so what I would do is I would just look at those values. Which of the following statements has to be true? Could 2 be the min value from 0 to 4? Absolutely it could be, right? You look at these two values right here and here. Yeah, it could be. However, could the function fluctuate between 0 and 1, or 1 and 2, or 2 and 3? Could it go lower than that? Absolutely it could as well. So that's out. Could 4 be the max value? Absolutely it could be. Is it 100% of the time, or must it be true? No. Could the derivative be greater than 0 for all values? No, absolutely not. The reason why is because you see that the function is going up then down, right? So that wouldn't work. And would the derivative always be negative for values between 2 and 4? It could be, right? It's going down from, let's say this is x equals 2, that output is 4. And then it goes to x equals 3, that output is 3. And then that output for x equals 4, sorry, that was my kid, is 2. So does it look like it's always negative? Yes. Could it have fluctuated in between? Could it have looked like this? Well, as long as it passes the vertical line test, yes. So that's out. Okay, it's not always true. So therefore it must exist. Due to the fact, right, that the slope of the secant line equals f of 4 minus f of 0 over 4 minus 0. Well, that's going to be 2 minus 2 over 4. Well, that means that f prime somewhere has to equal 0 between 0 and 4. So the mean value theorem comes into play on this problem.